Okay, so welcome everyone to this basic algebra course on group theory. So let me begin with the notion of group. So definition, a group is a pair G comma star where G is a non-empty set and star from G close to G is a map. It's called such a map is called a binary operation from G satisfying the following property. The first thing is that we want the star to be associative. This means that A star B star C equal to A star B star C for only A, B, C, G. Second thing we want is that existence of identity on neutral element. This means that there exists an element E in G such that A star E equal to A star A equal to A or A in G. The thing we want is that every element should admit its inverse. Existence of inverse for each A in G, there should exist an element B in G such that A star B equal to B star A equal to E. So in this case, B is called inverse of A. Okay. So a group is a pair. So basically a non-empty set equipped with a binary operation such that this binary operation should be associative. Every element and there is a distinguished element denoted by E, small e, which acts like neutral element means that A star E equal to E star A equal to A for A in G, and every element should admit say inverse with respect to the binary operation star on G. Then this pair, such a system is called a group. Okay. So let's see some of the examples. First example is the trivial group. So you take G to be singleton set containing only one element, say this, and set star to be the binary operation defined by E star E equal to E. Okay. Then G obviously satisfy the axioms of the groups. So uh, this is a group containing only one element, it's called a trivial group. Next example, group of order 2, say now that means order means the number of elements in G. Take G equal to say 1 and minus 1. Okay, and define a binary operation on G like a multiplication. Define on G by setting 1 star 1 equal to 1, 1 star minus 1 equal to minus 1, minus 1 star 1 equal to minus 1, and minus 1 star minus 1 equal to 1. So that means we can basically write this in terms of the following table. Minus 1, so 1 minus 1, 1 minus 1, and this is the binary operation. So 1 times 1 equal to 1, 1 times minus 1 equal to minus 1, minus 1 times 1 equal to minus 1, and minus 1 times minus 1 equal to 1 in this way. So such a table is called a Canny table. So you see that this set equipped with this obvious binary operation with a multiplication of real numbers, this forms a group. It's a group of order 2, okay, because it has the two elements. Example 3, you take uh, um, say group of order 3. Okay. So take G to be A, B, where the binary operation and define a binary operation on G by the following table. So star E A B E A B. So you define it to be A E A B A B. Okay. And here you take A square equal E time A equal to B, and so basically we want B to be A square and A B equal to Q equal to identity. So A B equal to identity, A equal to identity, and B square equal to A. Okay. So basically we want b equal to a square. So then b square and a cube equal to identity. So b square equal to a to the power 4. So what a cube equal to identity, a cube times a. So we want this to be b times a equal to a. So that's the idea. Okay. And obviously by construction we're making it to be this a b equal to b. So this is should be satisfied in this example. So we get a group of order 3. Okay. So next we see an example of a group of order 4 lines for group. This is denoted by K4. Okay. So what is K4? K4 has 4 elements V, A, B, C, where A square equal to B square equal to um, AB equal to C. Uh, all element AB equal to C. A square equal to B square equal to C square equal to identity. And we want AB equal to BC actually. And AB equal to BA equal to C. So basically that multiplication table is like this. A, B, C, star, A, B, C. So this make this like a square of B square equal A, B, C, A, B, C, A square equal to identity, B square equal to identity, C square equal to identity. And we want it to be C, so BA to be C, and CA to be B, and CA to be B, and BC equal to A, and CB equal to A. So this is the multiplication table we want. Okay. So this is the multiplication rule or the binary operation defined by this table for the group K4 lines for group. So you see that this satisfy the all actions for group. So this is a group containing 4 elements. This is called plans for group. Okay. Now next, let us see another example. Group of nth roots of unity. Takes an integer n greater than equal to 2 and let mu n equal to set up all z belongs to C such that let to be one n equal to 1. So, so this is a set of all nth roots of unity in C. So note that this forms a group with respect to multiplication, because if I take any two complex number whose raised to the power of r is 1, then the product also satisfy the same equation. right? So this forms a group with respect to the multiplication operation. Okay. So far we have given examples of finite groups. So now let's give you example of an infinite group. For example, you take Z. Additive group Z. Z is a set of all integers 0 plus minus 1 plus minus 2 plus minus 3 and so on. So this forms a group with respect to usual addition of complex of integers. Right. Next example is you take Q, a set of rational numbers E by Q such that E Q integers Q not equal to 0, the set of all rational numbers. So again, this forms a group with respect to usual addition of rational numbers. Okay. Similarly, I have another example. Similarly, R. Similarly, the sets of real numbers, complex numbers also forms a group with respect to usual addition of real numbers and complex numbers in case of sleep. Good. Now we consider another group. So group symmetries on a set. So given a non-empty set X, let Sx be the set of all bijective maps from X into itself. Okay. So then now we have a composition of two maps. Then define a binary operation on Sx by composition of two maps. So this is the binary operation. You take a bijective map F from X to X and you take another bijective map, you just compose it. So composition of the bijective map is a bijective map, so you get a element of Sx, right? So now note that this forms a group with respect to this composition operation. Called the group of symmetries of the set X. So, okay. So let's see a precise example of a group of symmetry on a set. So you take, for example, take X to be the set 1, 2, 3. Right? So basically, you may think this to be a triangle labeled as 1, 2, 3. Right? So vertices are labeled as 1, 2, 3. So then you can think about rotational symmetry of these triangles. So this gives a permutation on the set X measured by it maps. So X to X, you get a rotational symmetry. So let's see. So 3 goes to the position of 2 by say theta equal to pi by 2 pi by 3. So rotation by this angle theta, you get 3, 2, 1. Again, we apply this rotation, you get another triangle 3, 2, 1. And if you apply the same theta once again, you get back to the previous position 3, 1. Okay, so if I apply theta once, I get this one. And second time, third time, I get back this one. So therefore, this rotation has a property that its composition 3 times gives the identity element, right? So, and you can think about another kind of symmetry by reflection along the y-axis, right? Reflection about like this one. So you fix a y-axis, okay, and you look at the triangle, this equilateral triangle. So level as 1, 2, 3, something like that. So if I take a reflection along the y-axis, I get this reflection. I get 2, 3, 1. Okay. So if I apply reflection once again, I get with the previous one, right? So this has a property that is square is the identity. Okay. Reflection has a property that is square is identity, and rotation has a property that is square is cube is identity. Okay. Now, so basically, this gives us all possible bijection from X to. So this describes all possible bijective maps from X to X, where X is a set containing 3 elements 1 to 3. So now, note that from this description, you see that there are exactly 6 elements in this group as X. Thus, there are exactly 6 elements in X obtained by composition of all such maps. Okay, so more explicitly, you can write down such binary all such things like this way: 1, 2, 3. You send it to 1 goes to 1, 2 goes to 2, 3 goes to 3. This is the identity thing. And there is 1, 2, 3. This goes to. So maybe let us try to write it simply. So 1, 2, 3. So this is the domain of the map, and we denote its image in the below. So identity is 1, 2, 3. Then you take map 1, 2, 3 goes to 1 goes to 2, 2 goes to 1, and 3 remain fixed. Okay, and you take not this one. So this 1, 2, 3, 2, 3, 1. Take 1, 2, 3, 3, 2, 3, 1, 2. Okay, and then you take 1, 2, 3, 2, 2, 1, 3, 1, 2, 3. So these are the all the possible budget maps you can get. So these are the elements of SX. These are all elements of SX of x equal to 1, 2, 3. So we denote this, we denote it by S3. Okay. Similarly, we can define budgeting maps between any set containing n elements. So similarly, given an integer n greater than equal to, let Sn be the let Jn be the set 1, 2, 3 represent n, and set Sn to be all sigma maps Jn to Jn, so that sigma is bijective. Define composition map from Sn cross Sn to Sn by taking sigma and tau, send it to tau compose sigma. Okay. So this again gives a bijective map given a to bijective of sigma and tau, you get a bijective of their composition. So bijective map. So then Sn forms a group with respect to the composition of map. We call it set equal to n symbols. Okay. Now Let us discuss another important class of proofs. So this is as follows. Note that define a fix an integer, fix an integer in greater than equal to, and define a relation congruence modulo n for z by setting write like this. A is congruent to b mod n if a minus b equal to nk for some k in z. Okay. Then um, then it turns out that this is an equivalence relation because A is congruent to A mod n for all A in Z. That is clear because in this case A minus A equal to 0, which is multiple of n, right? So this this relation is uh, symmetric, sorry, reflex relation. So note that if A is congruent to B mod n, then B is congruent to A mod n, right? Because this means what? This means that A minus B equal to nk for some k. So this implies that B minus A equal to n times minus k. So minus k is also integer because k is integer. So therefore, this B is congruent to A mods. So this relation is symmetric. Now if A is congruent to B mod n and B is congruent to C mod n, then A is congruent to C mod n. Because A is congruent to B mod n means that A minus B equal to nk, and B is congruent to C mod n means that B minus C is equal to NL for some integers L. So this then by adding these two equations we get A minus C is equal to N k plus L. So this means that we get B is congruent. This means that we get this equation A is congruent to C mod n. So therefore, this is a transitive relation. So in particular, so it is reflexive, symmetric, and transitive, and hence this is an equivalence relation. So this is an equivalence relation. So once we have an equivalence relation, so then Z can be written as can be written as a union of these sequence classes. So now an equivalence class of A is of this form B belongs to Z, so that A is congruent to B mod N. So that means that B is Z, so that B is equal to A plus NK for some A and Z, right? So this set is nothing but this can be written as A plus Z, right? Okay. Now, not that given any A belongs to Z, so the division algorithm is unique integers. Say Q R with 0 less than equal to 1 less than n, such that A equal to NQ plus R, right? This R is called the remainder term. So from this, you say that A minus R equal to NQ. So that means that A is congruent to R mod n. So therefore, any integer is congruent to its class of residue upon divided by that residue for the division of that element by integer n, right? So now, how many choices of residue R you can get? Exactly 0 up to n minus 1, right? So therefore, any element is any integer is congruent to R mod n, where R lies between 0 and n minus 1. So therefore, the set, if I take a Zn to be the set of all congruent classes of integers modulo n, then this contains exactly the class of 0, class of 1, class of 2, and so on up to class of n minus 1, right? So there are exactly n many elements. So each of these elements can be enjoyed by the class of its residue modulo n. Okay. So now we can define a addition operation modulo n by setting the class of A plus class of B to be class of A plus B. Now there is a small catch that uh, might happen that the class of A equal to class of B. If class of A equal to class of A prime and class of B equal to class of B prime, then you have to show that class of A plus B equal to class of A plus A prime plus B prime, right? Then only this addition will be defined. Now from this we get that A minus A prime equal to nk, and from this you get that B minus B prime equal to nl from k l e z, right? And from this you get A plus B minus A prime plus B prime is equal to A minus A prime plus B minus B prime equal to nk plus nl is equal to n times k plus n. So the class of A plus B equal to class of A prime plus B prime, right? So this shows that this addition operation of Zn is well defined. Now it is easy to check that this set forms a group with respect to this operation. Note that this Zn with respect to this addition operation forms a group. Okay, okay, good. Another example. So consider the 6 n greater than equal to 2 and take G to be GLN R, the set of all n by n matrices with real entities. Okay. Now you define the multiplication operation on matrices. So then you get a binary operation GLNR cross GLNR to GLNR. This is the multiplication of matrix A comma B goes to AB, right? Note that with respect to this multiplication operation, this forms a group. So clearly, this multiplication is associative. There is identity element, namely you take the n by n identity matrix. So multiplication of A with identity matrix In is A. And given any invertible matrix, you can so complete its inverse, right? So therefore, GLN forms a group with respect to matrix multiplication. Then GLN forms a group with respect to matrix multiplication. Yes, yes.